All right. Okay, so last time, did a bit of course intro, talked about linked lists, and then started talking about stacks. Um, I think I'm gonna go back over the beginning parts of stacks just in case. I also think I maybe went through it a little bit too quickly. Um, so a lot of this might already seem familiar, but hopefully a second pass is somewhat valuable. Right. So stacks. Um, Stacks are an ordered collection where you can only insert or remove things from one end. We call that end the top. You might have also heard this referred to as like the last in, first out principle, or LIFO, where the last element inserted is the first element removed. Some examples of stacks in the real world, uh, you can think about like function call frames, right? So the most recently called function is the first one that returns. Um, if you have main and then main calls foo and foo calls bar, then bar was called most recently, so bar returns first, and then foo returns, and then it goes back to main. Um, and a stack of chairs, right? You can only pick up the top chair in the stack. Uh, and the most recent chair that you put on the stack is the first one that you take off. Um, Operations on stacks, we had push, which inserts an element at the top of the stack. You have to make sure that the stack doesn't overflow. And if it does, you have to do something to resize it. We have pop, which removes and returns the element at the top of the stack, right? So push adds something, pop removes something. Pop has to deal with the case that the stack might be empty. And we'll talk a little bit about different ways to deal with that. Similar to pop, we have peek, which returns the element at the top of the stack, but it doesn't remove it. Peek also has to deal with what happens if the stack is empty. Um, Now, like I mentioned last time, stacks are kind of uh, a principle or like an interface or something like that. They're not a concrete like implementation. Like there's not a single data structure that you could write like a struct in C that would be a stack. It's sort of given given a lot of different data structures, you can use them in a way that sort of implements stack semantics, right? So one way to concretely implement stacks is with a linked list. Here, the push operation becomes inserting at the head of the list. Right, so now we're thinking of the head of the list as sort of the top. Popping is deleting at the head of the list. And then peeking is just taking the value at the head of the list and dereferencing it. Um, Similarly, we can think of implementing stacks with arrays. Right, so for this, we pre-allocate a block of memory and we keep a pointer or an index or whatever to the current top of the stack. And this starts at just the beginning of the array. We'll call that the stack pointer. Right, so I have array, I initialize SP to 0, and then when I want to push, I write at array of SP, whatever value I'm pushing, and then I increment SP so that the pointer of the stack moves up. Um, for pop, I sort of do that but backwards, right? So I take SP is pointing to the top of the stack, or like what the next element's going to be. So I decrement it by 1, and that gets me the most recent element pushed onto the stack, and then I return it. And then peek just kind of dereferences SP minus 1 and returns that. Um, I maybe could have made this an attendance poll, but I didn't. So I'm not going to. But I am curious. Do people have any thoughts on why in our linked list implementation we chose to insert and delete from the head instead of the tail? Ah, yes, excellent. Why isn't push at the tail? Any thoughts? Messes with null too much. That's interesting. Could you say more about that? How might it mess with null? Hmm. Okay, minimize the amount of times you're trying to dereference nodes pointing to null. That's that's an interesting point. In theory, if we have our linked list implemented correctly, like it should be okay to write to or to try to like insert at the head or insert at the tail. But yeah, if you try to push at the tail, if you remember from the linked list lecture yesterday, uh, pushing at the tail, well, I guess inserting at the tail is fine, but removing from the tail means we have to iterate through the entire list to find whatever the previous thing was just before the tail, and then um, set that to be the new tail of the linked list, right? So um, inserting and deleting at the tail takes a bit more work. Uh, yeah, more error prone. There's more operations that you're doing, more chances for something to go wrong. So yeah, you could sort of do both, but generally we insert and delete from the head. Um, Next week, or maybe towards the end of this week, given how fast we're going, we might have some better language to describe that, right? So we might be able to say things like inserting or removing from the head of a linked list is constant time, and removing from the tail of a linked list is potentially like linear time. If that doesn't make sense right now, that's okay. We'll talk about that. That's like time complexity stuff. But there are sort of like uh, we can make this precise, right? We can be precise about what it means for one choice of top to be better than the other. So cool. Yeah, so we did talk last time about overflowing and underflowing, right? So uh, if we push into a stack implemented by a linked list, generally we don't expect a stack to overflow unless the operating system runs out of memory or something else happens. But of course, in that case, there's not much we could do anyway. Um, Conversely, if our linked list or if our stack is implemented by a linked list, deleting at the head can potentially cause an underflow, right? Because the if the head is if the list is empty, then the head is null, and so trying to delete it, we're probably going to dereference null. We're probably going to end up segfaulting. Um, can the array-based stack overflow? We decided that yes, it could, because at some point, right, we've allocated a finite amount of space in our array. And so at some point, if we push enough things onto the stack pointer is going to point to the end, or like one past the end, once the array is full. And so if we try to push something again, it's going to try to write outside of the bounds of that array. And that's going to give us undefined behavior. Um, and similarly, right, an array-based stack can definitely underflow, because if the stack is empty, then the stack pointer is going to be 0, which means if we decrement it, it's going to be -1. It's going to once again point past the end of the array, or I guess past the beginning of the array. And we're going to be trying to read from memory that hasn't been initialized or hasn't been allocated or whatever. So that's bad. So the thing to think about here, I guess, is like when we implement stacks, there are failure conditions that we need to keep track of. And maybe we have to do a little bit of engineering work to sort of make sure that they exit gracefully if something bad does happen. And maybe if there's a way to recover from the something bad, then we try to recover from it. I will talk more about that later in this lecture, but I just kind of want to bring that up. Okay, so maybe the words on the last slide weren't very convincing, or maybe you would benefit from a like visual example. So let's think about pushing to a linked list stack. Right, so here I've got my favorite linked list from the previous lecture. It's got 3, 6, 11. And I'm keeping a header that points to the head and the tail just for convenience, because we may as well, right? So if I think about the operation pushing 2 onto the stack, right? I can think of that as, if you remember from the last slide, pushing is inserting at the head. So I'm inserting this new node that contains a 2 at the head of this linked list called stack. If we unfold that one more step, we remember that insert at head means we take our new node, set its next pointer to the current head, right? And then we set the new head of the linked list in the header to the new node that we just created, right? And if I rearrange things a little bit, I can move new node down, and we see that we've got a linked list just like before, but now there's a 2 at the top. So hopefully this makes sense. Hopefully this is reasonably convincing that pushing to the head sort of, or that inserting at the head kind of like gives you push semantics on the stack. Conversely, if we try to pop from the stack, right, we decided that pop was deleting from the head of the linked list. So if I expand what deleting from the head means, first I grab the node that I want to delete, and that's going to be the current head of the stack. Then I advance stack.head by 1, so I set it to node to delete.next. And then I just return the value of the node that I was deleting. Now, if I was responsible for cleaning up my memory here or something like that, I might also want to, like if this was allocated on the heap, I might want to free it and just return the value. Or maybe whoever is calling this pop function expects the entire node, and so I return the node and I return like a pointer to the node and I expect the caller to clean it up or whatever. I have to sort of be careful about that when I implement these things. I have to make those semantics precise, but somehow this is essentially what ends up happening, right? Does a linked list thing make sense to everyone, or does the like linked list implementation of stacks make sense? Or are there any questions about that before we move on to the array example? I see a thumbs up. I see a couple thumbs up. All right, cool. I am going to move on. And again, feel free to type in the chat if you have questions, or just like unmute yourself and interrupt me and ask them, because sometimes I can't see the chat. For example, right now, I don't know how to bring it up. So if there's questions I'm missing in the chat, please just yell at me. Yeah, all right, cool. So if there's no questions, we will move on to the array example. Oh, there we go. Okay, so if you remember a stack or implementing a stack using an array, I said that we pre-allocate a block of memory. So here I've pre-allocated like 5 elements, and we have a pointer to the beginning of the array, which is the stack pointer. So it's the SP. If I want to, and the stack is starting off empty right now. So if I want to push 2 onto the stack, remember that was stack at SP++ equals 2. So I write the value to wherever the stack pointer is, and then I increment the stack pointer, right? So I've got 2 in there, and now the top of the stack is sort of pointing 1 past that, right? So I've sort of saved that 2, and the next time I try to push, it's going to write immediately after the 2. And so once again, we can see like pushing 3 onto the stack means I write the 3, and then I increment the stack pointer. Okay, so if I've pushed 2 and then pushed 3, if I pop, what do I expect the value popped to look like? Or what value do I expect to be popped from the stack first? Three. Excellent. 3. Yep. Good stuff. Yeah, okay. So popping means I decrement the stack pointer, and then I return the value that it's pointing to. And that happens to be 3. Now, thing to note, right? In our sort of abstract description of the semantics of the stack, we said that when we pop something, it should get removed from the stack, right? Uh, but you'll notice no part of this like popping instruction actually overwrites the 3, right? The 3 kind of stays there until we push something else. We just kind of think of the stack as not containing that, because we think of the stack as containing everything strictly to the left of the stack pointer, right? So if I were to, for example, push a 4 now, it would push, it would like over, the 4 would overwrite the 3 instead of going to the right of the 3 because physically the 3 is there, but morally we want to treat it as though it's not. Um, I don't know, maybe that's a sort of meaningless distinction to make, but I think it's important. So yeah, the 3 doesn't get overwritten. All right, now, as I kind of alluded to earlier, uh, the implementation that we have, question in the chat. We don't need to delete the value. Right, no, we don't need to delete the value. Well, okay, maybe let's go back here. Yeah. So we don't need to delete the value specifically because the stack pointer is already pointing to it, or it's already pointing like before it or something. And so the next time we push, it's just going to get overwritten, right? If we've allocated this entire array on the heap in one go, we'll free it once at the end. We don't have to like free every individual element in this array. It's not like a linked list where we need to do that. So from like a memory management perspective, that isn't as much of an issue. And then, yeah, like I said, there's no need to like zero that memory out or like replace it with some sentinel value or whatever, because as long as we're using our stack correctly, no one is ever going to read the 3 once it's been popped. Does that make sense to everyone? Are people convinced of that? What if we want to return the whole stack at some point in time? Will that ever be the case? Sure, it could be the case. If you do want to return the whole stack, then either whoever you're returning it to needs to know to not read past the stack pointer, or you kind of loop from the beginning up until the stack pointer and like write it into a fresh array and return that or something like that. It kind of depends on what you're trying to do with it. Or, right, you can like once you know that you want to return it, you can sort of explicitly go and say, okay, set the stack pointer to 0, move it all the way to the right, and set everything else to 0, and then it's fine. But I guess the like you are free to zero out the memory when you pop. It's just there's no need to a priori if all you're doing is pushing and popping from the stack, because the next time you push, it's going to get overwritten anyways. Okay, we're reading the array. The SP is not inclusive. That's correct. SP always points one past the last element, right? So it points at the current top of the stack or the current place that you would write a new element to, right? So if I go back here, I've already written a 2, so SP is pointing one past that 2, so that I can directly write to the location where it's pointing. You could consider like having it point at the current, like you could have it point at the 2 instead and then like increment it before writing, but then you would have to initialize like when the stack is empty, there's nothing there, right? So you would need SP to point like 1 before the beginning of the array, and that's kind of bad. That's kind of gross. So I think it's mostly just for that reason that we do this, or that we sort of treat it this way. But yeah, there's a lot of different ways that you could make the indexing and arithmetic work out, and it would probably be fun. Okay, so moving on. Right, okay. So if you remember, we had some errors here, right? The implementations we described earlier were kind of meant to work assuming that nothing was going to go wrong, right? So in particular, this can be a pretty strong assumption. For example, if we try to push when the underlying buffer is full, right? If we're implementing our stack with an array and you try to push and the array is already full, just doing array at SP++ is going to give us like at best a seg fault, at worst some kind of undefined behavior or some other like vulnerabilities or whatever, right? It could be pretty bad. If the OS runs out of memory for a new linked list node, not much we can do unless we're sort of expecting that memory to be there, and then we end up dereferencing null, or we end up doing something else that doesn't really make sense. And similarly, if we try to pop or peek from an empty stack, right? That could be bad. If it's a linked list, we could end up dereferencing null again. If it's an array, we could end up reading from memory that we haven't allocated. Yeah, potentially bad things can happen. Now, it turns out these aren't really questions about data structures, right? Like a stack is a stack regardless of whether you've implemented it correctly or not. Maybe that's too strong of a statement, but like these sort of edge cases are like things that you have to be concerned with in like in practice, right? When you're like actually implementing these data structures, you want to make sure that they are robust and not error prone, and you deal with that stuff correctly. But from like a theoretical analysis of stacks, right, we just sort of assume that we don't run into these bad situations. Nevertheless, since this is an engineering class, we should probably talk about the software engineering approaches to dealing with these errors, right? So in C in particular, we have a few options. When we allocate a new linked list node, right, you can check to see if the allocation succeeded. Does anyone remember or know how you do that? Like if I call malloc and the OS decides that it can't give me any memory, how would I know that? Yes, exactly. Thank you. Yes, you should check null. Malloc will return a null pointer if the OS was unable to allocate memory or refused for whatever reason, right? So in general, right, it's really easy to write programs assuming that nothing's ever going to go wrong. But in the real world, plenty of things can go wrong. And so you should kind of uh, program more or less defensively when things like that might be the case. Right. So when we allocate a new linked list node to push onto our stack, we check to see if the allocation succeeded. If malloc returned null, then we know it didn't. And of course, in this case, there's not really much we can do besides just abort the program. But at least we like do that, right? Like explicitly check to see if it's null, and then if it is, print out an error message and say like, oh, we ran out of memory or whatever, and then terminate. Um, instead of continuing on expecting that memory to be allocated and then getting into more issues. Uh, on the array side of things, if the array that if the buffer that we've allocated is full, we can allocate a new one, right? I can allocate a bigger one and copy stuff over. This takes some work, obviously, right? I have to allocate a bigger array. I have to like loop over everything in the existing array and copy it all over. There is a nice realloc, which will kind of, I think realloc just allocates and then does a mem copy for you and then returns the new pointer. It's doing the same stuff under the hood, but maybe it's a little bit faster. But yeah, we have to somehow, right? We have to reallocate. We have to move our array into a bigger array. And then when popping from an empty stack, of course, the easiest thing to do is just abort, right? End the program, print out an error message that says, hey, you tried to pop from an empty stack. That doesn't really make sense. But there are, at least in C, other error handling strategies that we can use. I'm going to take a little detour into that. Error handling in C. So one sort of easy thing to do is to use assertions, right? So assert is a macro defined in the header assert.h. It checks a condition at runtime. So this can depend on like dynamic variables. This can depend on whatever you want. Just give it some Boolean value. It checks the condition and then it crashes the program if the condition isn't met. This is good for like debugging, I guess. If the rest of your program relies on some invariant being true, like for example, if you call malloc, you expect the pointer returned from malloc to not be null. The rest of your program assumes that the pointer returned from malloc is not going to be null. So you can assert that the pointer returned from malloc is not null. And that way, if it is, the program will just crash, right? Crashing is good. We want things to crash when things are wrong, because if they don't crash, that means our program is running in some undefined state, and that's bad, right? So we can use assert to kind of make sure that that doesn't happen. There's a runtime overhead, right? So you use this in like a debug build, or I think if you GCC might just like optimize this to be a no-op in release builds or optimized builds or whatever. But right, that's sort of something to keep in mind. Alternatively, exit codes, right? So you can call the exit function with a return code. This is just like returning from main, but you can do this from any other function and it'll immediately terminate the program and return with that particular return code. So similar to assert, this terminates the program early, so you don't keep executing code after you've like seen that an invariant isn't met. But unlike assert, this is sort of good for errors that you are expecting to happen or that you think might happen, since now you can report the error code back to the user, right? So if you've got a program that opens a file and it relies on user input for like some file name or like file path or something like that, it's sort of an expected error, like failure mode, that the file might not exist, right? So you check to see if the file exists, and if it doesn't, you return a return code. Or you call exit with some like file does not exist return code, and then the user can sort of look at that and say, oh yeah, I see the file doesn't exist. Okay, yeah. So these make sense for unrecoverable errors. Popping from an empty stack should maybe not be unrecoverable, right? There are maybe ways that we can recognize that we tried to do that and then walk it back, or fix our assumptions or something like that at runtime. So let's talk about recovering from errors. The problem is C is not great at error handling stuff, mostly because it's trying to be like a low-level language, and so it doesn't give you these nice features like exceptions. But there's things we can do. Right. So first of all, we can set error no. I guess that means error number, right? A lot of I don't know, like POSIX functions do stuff like this, right? So for example, here you create a global variable called pop failed. If you pop from an empty stack, then you set pop failed to be true, or set it to 1 or whatever, and then you return some nonsense value, right? You can return whatever you want. This leaves it up to the caller to remember to check pop failed every time they pop, right? So you can't just write pop from the stack anymore. You have to pop from the stack, and then if pop failed, then handle that case. Otherwise, use the value that you popped. So it's a bit more work, but it allows us to sort of signal back that something bad happened as long as the caller remembers to check. Similarly, we can return an error code directly from the function, right? So instead of returning an integer value when we pop, we can return this struct pop result. This contains a success flag and an integer value. You pop from an empty stack, return false for the success flag. And then again, whatever garbage value you want. And then the caller just has to remember to check the success flag before using the value returned. There's a lot of other ways that we can signal failure to the caller. A lot of these still rely on the caller checking for failure, right? So for example, we could, instead of returning both things in a struct, we could just return a Boolean that says success or failure, and then have our pop function take in a pointer to the value, or take in a pointer to where it should write the value if it was successful. And then if it's a failure, we don't have to like return a garbage value or whatever. We just don't overwrite value. Again, a lot of like POSIX functions are implemented in this way. So you'll see like these sort of like out parameters where you like take the address of the variable that you want the return value to be stored in, you pass it into the function, and then the function doesn't actually return anything meaningful except for an error code, and then it kind of just sets the pointer on a success. Alternatively, you can, I call this like rolling your own exceptions, right? So if you're familiar with C++ or Java or something, these languages have like exception handling where you can like run a block of code, and then if a particular kind of error happens in this block of code, you jump to something else that knows how to handle it, and then you clean it up. C has these functions called set jump and long jump, which basically unwinds the entire call stack and directly jump to a new location. What I mean by unwind the call stack is it's not like calling a function where it'll then like go back and like it won't return control flow back to the caller. It'll just jump to that new location. Um, so you can, for example, write an error handling function using set jump, and then in your pop code, if pop fails, you call long jump, and then it'll jump to that error handling function. This is kind of like go-tos as well, right? Um, that way the caller knows if control flow ever returns to them, right? Like if you call the pop function and you ever like if your code continues executing after calling the pop function, that means that the pop succeeded. So you don't have to remember to check anything, right? If pop failed, it'll just never get back to you. Um, so that's nice. The problem is you have to kind of be careful with this, right? If control flow never gets back to, oh yeah, we could go over long jump again. It's yeah, it's a little bit weird, right? Basically the way these work is set jump sets a location in your source code or in like the yeah, it sets a location in your source code to jump to when you call long jump, and then you call long jump if pop fails, right? So you say like if the stack is not empty, return like pop from the stack and return that value. Otherwise, long jump to that like pop error handler. And that way, whoever called the pop function would never like the pop function would never return back to whoever called it if it failed because it would immediately jump to the error handler. Um, and that way, if you write uh, like you can write code basically assuming that that pop succeeded because if it didn't, then you wouldn't be running that code. Yeah, it's like a go-to function. Um, like I said, though, you have to be very careful with this sort of thing. For similar reasons as to why like go-to is kind of bad, it kind of obfuscates the control flow. And then also, the caller might have stuff to clean up, right? Like I might allocate something on the heap and then call pop and then free something on the heap, like free the thing that I allocated. And to me, that looks fine. What I don't know is that pop might secretly never return to me and it might go somewhere else entirely. And now all of a sudden I've got a memory leak, right? So um, that's bad. So you sort of have to be careful. Right, that's the difference. It does not save the return location. Um, long jump does not save the return location. And that's kind of intentional, right? That way it doesn't return back to the uh that way pop never has to like send a return value back to main. Um, that's yeah, that's the idea. Um, you maybe might not use this, and that's fine. I just figured I should mention it because it's a thing that exists. Are there more questions on the error recovery stuff? Or does this kind of make sense to people? All right, I am going to move on. Okay, so we talked a lot about how to deal with errors in pop, right? Mostly because if your stack underflows, you have to do something about it. Um, in the case where the stack is backed by an array, uh, we need to dynamically reallocate more memory, right? Now I'm using the word more, just kind of very, very loosely here. Uh, of course, the question is how much more, right? There's a couple of options here. We could increase by a fixed size every time. So I could start by allocating a block of 16 elements. And then when that overflows, I can allocate 32 elements, copy the 16 over. When that overflows, I can allocate 48, copy the 32 over. And so every time I allocate 16 more elements. Um, Instead of that, I could like double it every time or increase by some kind of multiplicative factor, right? So go from 16 to 32. But when that overflows, I go to 64 instead of 48. And then I go to 128 instead of 80, I guess, right? Or instead of, yeah, yeah. So I could double it every time instead of just adding 16. I could do basically any other growth rate I want. It turns out this might not be obvious unless you've seen like amortized analysis already. It turns out growing exponentially is better than growing linearly. If you grow linearly, you get something called amortized linear time. And if you grow exponentially, it becomes constant. We'll talk more about that next week or probably later this week. But I just kind of wanted to put that out there that like these are possible strategies for growing the stack. So hopefully by now you should know how to implement a stack using an array, using a linked list, how to handle errors, how to grow. You can shrink, obviously, right? If you pop enough things, you can decide to shrink the stack. Sometimes that's worth it if you're like memory bound. Often that's probably not worth it, which is why I didn't really mention it here. But yeah. Before I move on to the next thing, which is going to be queues, do people have questions about stacks or linked lists or course stuff that we've covered so far? Stop sharing. Is any error handling method favored? Do you mean in general or like in the class? In general, so I think it depends on what kind of error it is, right? If it's something, if the error is unrecoverable, but it's something that the user could potentially do something about, then you probably want to return an appropriate error code. If the error is somehow recoverable, like it's something that the programmer could do something about, then you don't want to crash the program. You want to somehow like check for that error condition and then make sure that your code handles it correctly. Um, if the error is something that you never expect to happen, and if it's happened, then something has gone terribly wrong, then you just want to abort, right? You can use an assertion for something like that. Yeah, so I think it just kind of depends on what what kinds of errors you're looking at. Yeah. Also, for the class, there's not really a preferred error handling method. Um, some of our programming assignments might ask you to like, there might be some edge cases where you have to deal with things going wrong. Like you'll have to sort of handle that gracefully. Um, in those cases, you're sort of free to decide how you want to implement your error handling. Um, the thing to remember, of course, is like you are graded both on correctness relative to the test cases and your memory management. And so if if you do your error handling inappropriately in a way that causes you to skip over your cleanup code, you will lose points because you will have a memory leak. Um, so I would just keep that in mind when you're deciding how to design things. Are there other questions about linked lists or stacks or error handling or anything we've covered so far? All right. If not, I will move on to the next lecture. Okay. Mm, oh, this is, there we go. Okay. Hopefully that's visible. Um, all right. So we talked about stacks. Now we're going to talk about queues. Queues are in some sense like dual to stacks, in the sense that they kind of work backwards, right? So queues are ordered collections where elements are inserted at one end, called the back, and removed from the other end, called the front. So if you remember in stacks, we insert and remove from the same end, and we call that end the top. In queues, it's kind of the other way around. Um, So in particular, you'll see like FIFO queues, right? First in, first out. The first element that we insert is the first element that gets removed. Uh, for example, the line at Starbucks, right? When you go to Starbucks, you join at the back of the line, and the first person in the front of the line, the person in the front of the line is the person who got in the line first, and they get to order first, and then it sort of proceeds that way. New people join at the back, and then people get served at the front. So that's a queue. Also, event queues, right? They're called queues for a reason, right? If you click a bunch of times really quickly, the clicks get processed in the order that you clicked them, uh, because they get pushed into this, or they get like queued into this event queue, and then they get dequeued out of the event queue. Anyway, yeah, queues are good for things where you want to like preserve the order. Um, okay, so we talked about operations on stacks. Queues have similar or like a dual set of operations on them, right? So we've got in queue, there's a lot of vowels, there's a lot of U's and E's kind of all over the place. So sometimes you'll just see this abbreviated like N and then just the letter Q or like DQ, something like that. Um, I like the vowels. I like how they look. I'm gonna write out in Q every time. But yeah, okay. In queuing, it's the queue equivalent of pushing, right? So instead of pushing an element to the top of the stack, we are inserting an element at the back of the queue. And as with stacks, we have to make sure the queue doesn't overflow. Dequeuing is like popping, right? So we remove the element at the back of the queue and return it. Similar to popping from a stack, we need to deal with the case that the queue is empty. And then with a stack, there was just one thing we could peek at, which is the top of the stack. But with queues, there's like two ends where interesting things are going on. So we can peek at the front or the back of the queue. So we call that front and back. And again, we have to deal with the case that the queue is empty. Similar to stacks, queues are kind of a paradigm or like a discipline or an interface or something like that, not a concrete implementation. So we can implement them with a linked list or an array, right? So if we implement them with a linked list, we enqueue by inserting at the tail, we dequeue by deleting at the head, and then the front and the back is just dereferencing the value at the head of the list or dereferencing the value at the tail of the list. So here, the tail represents the back and the head represents the front, which kind of makes sense. I think I asked this a little bit later. Actually, I think I was planning on going slower through these slides, and so I expected this to be another attendance poll, but it might not be. Thoughts on why we don't flip this around, why we don't insert at the head and delete at the tail? It's very similar to what we talked about for stacks. Yep, still time management, still deleting at the tail is expensive because we have to find the thing just before the tail unless we're using a doubly linked list. And so in the case that it's a singly linked list, we prefer calling the head the front and the tail the back. For arrays, or to implement a queue with an array, another question in the chat. Yeah, okay. So if you a header works for telling us where the tail is, it doesn't tell us where the element just before the tail is, right? So if you remember what delete tail looks like for linked lists, we delete the last element, but then we have to update the header to point to the new tail. And the only way to do that is by looping through and finding what was just before the tail. Because in general, our linked list only has a next pointer. If we have a doubly linked list with a previous pointer, then we can just set the new tail to be the old tail dot previous. But then that's a doubly linked list. Does that make sense to everyone? Any other questions? All right, cool. So for an array, again, we pre-allocate a block of memory. Now instead of this is an array, then won't the memory be adjacent? Oh, so for a linked list, so if you implement a queue with a linked list, you have to do deleting at the head for dequeuing and inserting at the tail for inqueuing. If it's an array, it's different, right? I'll explain what it looks like for an array. So similar to the stack, right? We pre-allocate a block of memory. Instead of just a single stack pointer, now we have a front pointer and a back pointer. We'll initialize both of these to point to 0. In queuing, we write to the back of the array, or we write to like array at back and then increment back. Dequeuing, we write to array at front and then increment front. So it kind of grows forward both ways. Dereferencing the front and back is just dereferencing the front and back pointers, which is fine. Now you might notice the pointers just keep increasing. Yes, front and back both start at 0 for the array, and the array is pre-allocated to a fixed size. But yeah, I think maybe you're kind of getting at the issue here, which is that these pointers just keep increasing, right? They never go back down. If the only thing I'm doing to front is incrementing it, and the only thing I'm doing to back is incrementing it, then at some point, both of those are going to go off the end of the array, even if my queue isn't full. And we'll come back to that. Yeah, so like I said, I timed this poorly, I guess. This was going to be an in-class poll. I think after lecture is over, I'll open a poll for it on Brightspace, and you can write the answers there. I won't have it require a file this time, although I did like some of the files that you all sent in. It was cool. Pictures of Kirby. That's nice. I like that. Okay, so yeah, we talked about that. All right, so again, enqueuing to a linked list. If we enqueue, we remember that was inserting at the tail. There's 3 steps to inserting at the tail. We set tail.next, or we set the current tail.next to be the new node. We make sure that the new node.next points to null, and then we update the tail in the queue's header. Right? I can rearrange that, and now it looks like a linked list with 2 enqueued at the end, or at the back. Now if I dequeue, unlike in a stack where I pushed 2 and then I expect to pop 2, if I dequeue after doing this, what do I expect to be dequeued? Three. Yes, thank you. Great. Because 3 is at the front of the queue. So dequeue is delete head, which has 3 steps. So I start by grabbing the current head of the queue. I advance head by 1, and then I return the value that I was going to delete. And again, right, I might the dequeue function might free the node itself, or like save the value, free the node, and then return the value, or it might return a pointer to the node and expect the caller to free it, or it might do something else. You might like allocate this in an arena somewhere, and you don't have to worry about freeing it or whatever. So these are kind of like abstract, perfect operations that don't deal with the nastiness of like managing memory and handling errors and doing all of that stuff. Something to think about, right? Don't just transliterate this pseudocode into your actual queue and stack implementations, because you will likely run into issues. Okay, the array is significantly more complicated than it was for the stack and than either of the linked lists were, I think. So if we try to enqueue 2 into our queue backed by an array, right, we write to wherever back is pointing, right? So in particular, front and back both start pointing at the beginning of the array, so they both start at 0. I start by writing the thing that I'm enqueuing into the back, and then I increment back. Right, so now front still points at 0 because I haven't dequeued anything yet. Back now points at 1. If I now enqueue 3, right, same thing. I write to where back is, which is now at 1. So I write there, and then I increment back. So back is now 2, front is still 0. Now if I dequeue, again, unlike with a stack, I don't want to dequeue the 3, I want to dequeue the 2, which conveniently is exactly where front points, right? So I just return whatever is at q.front or q at front, and then I increment front. Now, again, as I sort of mentioned earlier, the fact that we keep advancing the pointers means that that spot that had the 2 is never going to be used again, right? So unlike with an array where after I pop, I've still got the value there, but the next time I push, it's going to overwrite it, and so it's fine. I'm not like wasting any memory. With the queue, the next time I write, I'm going to write to back. The next time I read, I'm going to read from front. And everything is just going to keep moving to the right. And so every time I dequeue, I'm going to get another element of my array that's still allocated. It's not being used, but it's never going to be used. So my effective array is like shrinking every single time I use it. And that's bad. And so it's time to fix this, right? Time to fix the thing we said we'd fix. So first attempt at fixing it. If you notice, every dequeue operation makes the location that you dequeued from inaccessible, right? So if we go back here, we dequeued from the first element of the array, and so the 2 is now inaccessible, right? I mean, we can still access it in memory, but like the queue is never going to touch that spot again. So every now and then, we can just reset, right? Whenever the front pointer gets past a certain threshold, copy everything back, and then update, like move everything back by front, right? So for example, here, if we decided that now is a good time to copy everything back, we would move the 3 back to overwrite the 2. We would move front back 1. We would move back 1, and we would basically reset it. And that way, the next thing that we enqueue. How costly in time would a shift be? Yeah, so it would be, you would have to do 1 copy for every element currently in the queue. So if the queue is really big, this would take a lot of time. If the queue is really small, it won't take very long at all. Right? Yeah, so this is, in fact, a lot of extra work. If we don't expect it to happen very often, it's probably fine, right? If out of like the 10 million operations I'm doing on my queue, if once I have to copy maybe 1,000 elements, that's not the end of the world, right? Like that's fine. And maybe based on how I'm using the queue, I know that this is not going to happen very often, right? If the thing I'm using the queue for is like, if I know that what I'm going to be doing is inserting a bunch of stuff at the beginning, doing some operations, and then removing everything, I don't have to worry about inserting after removing, and so I don't have to worry about like this space getting wasted, and so I don't really have to worry about copying everything over. But if I'm modeling something like the Starbucks line, right, people are getting in and out of line constantly. And so I would need to copy very often. And so that becomes pretty bad. So yeah, this is sort of the easy way to do it. It's a lot of extra work. We can, in fact, do better by making our lives a bit more complicated. The better attempt is something called ring buffers. So the idea here is instead of treating our array indices as just indices into the array, we use them mod n, where n is the number of elements we've allocated, right? So here we have 5 elements. So I think of instead of thinking of front as an integer, I think of it as an integer mod n, which means that when front gets set to 5, I think of it as going back to 0. When it's 6, I think of it as going back to 1, and so on. People are comfortable enough with mod, right? Or is that something I should go over? All right, cool. Yeah, okay. So yeah, a pointer that goes off the end of the array wraps back around to the beginning. And in particular, this means that the locations that we dequeued out of are no longer inaccessible, right? We dequeued out of 0 because front got moved up to 1. But even if now that we're treating things mod n, even if we only ever increment front, we will eventually get front back to 0 because eventually it's going to go to 5, which means it's going to fall off the end, which means it's going to wrap around to the other side. So it's a little bit weird to think about, but you can sort of think of it as like taking the ends of your array and gluing them together so that if you go off the right side, you come back around to the left side. Yeah, so locations that get dequeued out of are no longer inaccessible. We do need to update. What if we grow the queue? Will the mod value have to change? Yes, the mod value will have to change, right? So if I grow the queue, if I fill up my queue of 5 elements and I decide I want to double it up to 10, then I have to copy everything over into the 10. I can probably just copy it at the beginning, no matter where it is right now. And then now I think of my indices as working mod 10, right? If I double it again, I have to think of them as working mod 20. So yeah, and n changes every time we grow the queue, or every time we change the size of the queue. Of course, we do need to update our enqueue and dequeue operations to account for this modular thing. Now, instead of just doing array at back plus plus equals value, we write to array at back, then we increment back, and we take it mod n, and so it wraps back around to the beginning. Same thing for dequeuing. Instead of just returning array at front plus plus, we grab the value at array of front, we increment front, reduce it mod n, and then return the value that we grabbed. Now is empty becomes instead of like, so normally, right, our queue would be empty if wait, how do I go back? This is wild. Okay. I don't know, is it still sharing? Yeah, it's still sharing. Okay, cool. All right. Well, anyway, if you notice, originally it was very easy to tell if our queue was empty, right? It's just front equals back. With the ring buffer approach, we have to make sure that they equal 0 mod n. So one could like front could move up to 2, back could be incremented around like 7 or something, and they would still be equal mod n because 7 mod 5 is still 2, right? So we have to put mods everywhere basically, but ring buffers kind of fix this this problem. Of course, we do still have to resize the array if the queue legitimately gets filled up. Yeah, that's fair. If you're reducing mod n every time, then it's probably not going to matter. If you just increment front and then you just do value equals array at front mod n, then it might matter. That's fair. Yep. But yeah, so to clarify, we do still need to grow the array if we fill up the queue legitimately. This just like ring buffers just prevent this like pathological case where we insert and then remove and then insert and then remove and insert and remove. And every time the queue goes back to having 0 elements, like every time it goes back to being empty, but it it kind of like consumes all of the original, like all of the earlier indices, and it kind of runs out of space that way. So ring buffers fix that. But if we legitimately try to enqueue 6 things, we're going to have to resize. Yeah. Are there questions about queue things so far, or about ring buffers, or anything else about the mod? All right. Oh, I guess it is past the end of class. Maybe I'll finish this up really quickly. We've got decks, which are double-ended queues, support inserting and removing from both sides. You can use these to implement a stack by only inserting and removing from one side, or you can implement a queue by always inserting and removing from opposite sides. You can also implement them with an array. Class is an hour, right? 8:40 to 9:40. Are my times wrong? Yeah, it's an hour. Okay, actually, I think I will just end it here. I don't know when the recording stops, so I don't want to talk about a bunch of stuff that the folks watching the recording can't see. Okay, so yeah, like I said, I will open a thing on Brightspace. The attendance poll question was why don't we flip the head and the tail of the list when why don't we enqueue at the tail and then or sorry, why don't we enqueue at the head and dequeue from the tail? Why do we do it the other way around? Um, yeah, you can also probably look at the recording, or I'll post the slides as well. Uh, cool. Yeah. All right. Sorry for going over. Thanks for coming. I will see everyone tomorrow. Submit it to Brightspace. I'll make an assignment on Brightspace for it. Do that right. Just the one for today. And there was one from yesterday.